Hello. In this video, I want to look at finding a confidence interval. So, finding a confidence interval essentially begins with a formula that we use the sample mean x bar plus or minus a critical value that we call z sub alpha divided by 2 multiplied by the standard error, which is sigma divided by the square root of n. Now, in either case, what would be given is that the mean happens to be unknown, and that being the population mean. So we want to be able to estimate them using perhaps like the sample mean, the standard deviation, and given some type of sample size, for example. So let's say that we begin by looking at a assessment of which that we saw that a standard calculus exam, it had that the standard deviation was approximately, or just given to be 3 points in this case, of which that we have x bar. Well, x bar will be the sample mean of a given standard calculus exam, which accordingly is 68. And in this case, let's suppose that a sample mean was based on a sample of 36 sample size. So here we have that to determine the value for the mean, the true mean, then in that case we can construct a confidence interval. So let's say that we wanted to know a 90% confidence for our confidence interval, where we use that in this case, what is alpha? Well, alpha is going to be determined by taking 1 minus 0.9, which is going to be equal to 0.10. So we have that this is our value for which alpha would be. And to better kind of visualize this, you could think of it in terms of like if you have a standard normal curve and you have that, for example, like here is your critical value but negative, and here's your other critical value but positive. But in either case, you have that you would have the 95% confidence or proportion between these two values. So what that would mean is that essentially you're taking alpha and you're dividing it into two portions, of which over here this would be 0.10 divided by 2, which is 0.05. Similarly, the area that you'd have to the left of our negative critical value would be 0.05. Now in this case, that means that sure, we'll try to find what is z sub 0.05, because we're taking the alpha and just as you see we're dividing it by 2. So to do this we would have to take the inverse norm. Now in this case we have that the area to the left over here is 0.05, so we'll use that it's going to be 0.05 but plus this middle area, of which this middle area in this case is going to be 90%. Yes. So that would be 0.9. So 0.9 plus 0.05, that's equal to 0.95. But what is the mean going to be? The mean is going to be 0, and the standard deviation is going to be 1. Now let's go ahead and calculate how we can find that critical value. So we'll just go to second vars. We'll use the inverse norm function. And here we're going to use the area to the left of our critical value is 0.95, with the same mean to be 0 and 1 respectively. And we're going to select left. Now in this case, it tells us that the value of which that we're going to use for the critical value is 1.64, let's say 5. So in this case, we're going to say that this is approximately equal to 1.645. Okay. Now, in any case, what we'll need to do is we'll just plug in what we know. We know that the x bar is 68 plus or minus. Well, in this case, you'll take 1.645. You'll multiply that by 3, but you'll divide that by the square root of 36. Now, if we want to compute basically that margin of error, we can actually just take 1.645, multiply by 3, and divide that by the square root of our sample, which in this case is 36. We hit enter, and it's 0.8225. So this value that we're getting, it's the sample mean plus or minus our margin of error, which we found to be 0.8225. So from here, what you could do is you could just take 68 minus our margin of error, and in any case we have it right here, and that would be minus the answer choice, of which we have that that's approximately 67.2. So in doing that, we'll get that that's 67.2, comma, well, if we add it, in any case, that's going to be 68.8, and here is basically our 90% confidence interval. And we see that essentially that the mean lies somewhere in between here. But what if we wanted to increase the value of the confidence so that way we could probably come up with a better estimate? Well, in that case, then, that would mean that if we're looking at a 95% confidence, then in that case, alpha is equal to 1 minus 0.95, which is equal to 0.05. Now notice that in either case, what is the critical value for alpha? Well, it's going to be the 0.05 divided by 2, which is 0.025. And then how do you find that? You use the inverse norm function that inputs basically that the area is going to be basically the 95% plus the alpha divided by 2, which would be 0.975 with a mean of 0 and a standard deviation of 1. So here we basically will see that if you take second inverse, or second var's inverse norm, and we put 0.975, then it does give us exactly the same critical value that we wanted, which in this case could be 1.96. So we have that this critical value would be 1.96, meaning that basically you have the same thing, 68 plus or minus. Well, instead you're using 1.96 multiplied by 3 and divided by the square root of 36. But let's go ahead and compute that, for example, and say that, well, we can take the margin of error to be calculated as the critical value times the standard deviation divided by the square root of 36. So we hit enter, and we get 0.98. So that means that with a sample mean of 68 for the average on a standard calculus exam, if we subtract the margin of error, then that's 67.02. But if we go ahead and we add, then in that case, like if we take the sample mean and we add the margin of error to be 0.98, then in this case we have that it's 68.98. So essentially we have basically our confidence interval at 95%, which will be, we said, 67.02 with a 68.98 average. So here we see that this is the confidence interval that we have for basically our point estimate mu in this case. So notice that what happened when we increased the confidence, the interval widened, basically, or it got wider. And in any case, if we were to explore, like, what happens if we look at the sample size of, let's say, if we make the sample size to be 100, or what if we make the sample size be 25, like what would happen to the confidence level if we were to look at that, for instance. And note that we could probably just say, well, let's use the calculator and find how to get a confidence interval much quicker, or quicker. So we'll have second vars. Here, actually it's not second vars, but it's stat. And you go to calc and you will select z interval. And here you're just inputting the statistics. So the standard deviation was 3. The sample mean for a standard calculus exam was 68 accordingly, and the sample size was 36. The confidence level we're saying was 0.9. So let's look at what happens if we use 100, for example. And let's go ahead and just hit enter. And see how we have 65.07, 68.49. Now, in either case, that means that with a 90% confidence with a sample size equal to 100, the confidence interval was 67.507, 68.49. 493. Okay. So here we see that if we were to look at what exactly is happening to the margin of error, well, basically we have that the margin of error, it's basically decreasing essentially, because you have that you made the sample size much bigger, which means that the margin of error is actually going to decrease. So we have that decreases. But if we look at, for example, like what were to happen if we, for instance, construct a confidence interval, and here we'll go ahead and say, well, why don't we just make the sample size smaller? Okay, so we can do this, and if we hit enter, so if we hit enter, and okay, so here our margin of error actually increased, actually. So we have that the margin of error has increased for this one. So we can write that down, that with a 90% confidence with n equal to 25, we found that basically this was 67.013, 68.987, and here the margin of error actually increased for this one. Okay. Now, of course, if you were to look at a smaller confidence, then of course that's going to mean that the confidence interval may actually get smaller, but 80%, that may be kind of stretching the point estimate, if that makes sense, that that you'd be 80% confident that the point estimate falls within that given range, for example. So it is likely that you could change the confidence level. And in any case, to do it, you look for the critical values in either case. So really, if you're given the sample mean, you know that you'll just plug it in. And then, of course, if you're given the confidence level, you just plug it in. And then, of course, the standard deviation, that would be known, and also the sample size in this case. Now, note that, for example, you've already determined what is the confidence level that would give you the critical value. So in this case, you already know that the Z alpha over 2 for 90% confidence is 1.645. But you also know that for a 95% confidence rate, that the Z alpha over 2 is 1.96. Now, suppose that if, for example, you looked at maybe like 98% confidence or even 99% confidence. Well, if we looked at a 99% confidence rate, then in that case what you could do is just second vars and go to inverse norm, and instead of using, like where we say left, what we can do is just account for it just by telling the calculator to just center the region such that we'll have an basically like the symmetrical, like the negative critical point and the positive critical point, of which hitting enter, we get that the value that gives us a 99% confidence is 2.58. So for that, we can actually just put that the 99% confidence for this one. And mind you that you would know that alpha is 0.01 divided by 2, which in any case will give you 2.58. So these numbers actually, if you were to, for example, use that the critical value for 90% confidence, if you were to round it to 1.65, that would be okay actually. So we can use these as our confidence rates, or our critical values in either case. So 1.65, 1.96, and 2.58. Okay. And keep in mind that if possible, we could actually find what would be our point estimate for our mean in either case, because we already have the lower bound and we already have the upper bound if you think about it. So either way, we can actually construct the point estimate for the mean, because essentially you're just finding that the mean is less than x bar plus the critical value and multiplied by the standard error, but then that's going to be greater than basically the x bar minus the critical value times the standard error, and then we have it. But how do you find the mean, the population mean? Well, you could probably just add these two and then divide by 2 or take the average in either case. Keep in mind that if the central limit theorem says that the sample size has to be greater than or equal to 30, then in this case we kind of already have an idea of like what critical values that we would be using or what kind of interval that we'd be looking at, for example. And that's the one that deals with the standard normal distribution in either case. So take into consideration that, though, if we knew the margin of error, but we didn't know the sample size, we could actually still calculate it, actually.